This is stuff you guys actually will probably might use.
What?
Really?
Problem might. Problem. I hope so. What's the probability?
50-50. So what I mean by that is, as we start looking at what's called a normal distribution, this is what we call the bell curve. This is where we get what's called standard deviations. What happens now is that as you guys have probably taken some of your standardized tests, you will see that there's like what they call a mean, an average, a standard deviation where you are placed within a standard deviation. That's telling you basically that when you have a normal curve, half of the data is on one side of the mean, and the other half is on this side. And then it breaks it down into what are called standard deviations. And you get all these different percentages of what is occurring within certain data sets when you know the number of pieces of data. So we're going to have what's called the normal curve, the normal distribution. And then we could have the paranormal distribution.
How long have you been laughing at that joke?
Ever since I found that. Thank you. It's like it's actually a genuine good one. Not like Murphy, roll your eyes. It's actually a.
It's an e-slap, bro.
I mean, well said. So anyway, so what happens with this normal curve stuff? Blood drive. As curves become normalized, yesterday you probably saw we saw some of that data set where things were skewed to one side.
Yeah.
As things start to become what's called more normal, you get this approximation. You're going to get really clean values. And we can say things are, once we say that something is normal, you get these percentages that always occur. And this takes a second to get used to, and it is so simple once we look at it. When you have a normal curve, whoa, you have a mean, the halfway point. That cuts it into two data sets. You've got 50% on one side and 50% on the other side. The total area whatsoever underneath that curve is all of your data, so the total area is always going to equal 1, because we're talking about percentages. You are under the curve. They say that 68% of total data occur within what's called one standard deviation. One standard deviation of the mean. Excuse me. So the distance between these two would have been 68%. Or as you start to look at it, 34% occurred here, 34% occurred here. Start thinking of this in terms of test scores, and I'll show you some examples how this works with scoring. This is where that comes into play. If the average on a test is 70% and their standard deviation is 10, that means that 68% of all data occurred within 80 and 60%. That's what that means. As you go further along on that, within 2 standard deviations, 90% of all data occur. Or excuse me, 95% of data occur. Which means 2 standard deviations. Now if you start playing around, hi! How are you guys?
Pretty good.
How'd you do on your Alpha 2 Olympics? Did you get better than 3?
I think so. I'm in second place. Yeah, I'm in ninth place.
Steal this pencil. Then you can't win. Good luck. Good luck, Richie. No, I do mean it, Richie. Richie, you can do it. Richie, come back. So, start thinking about what happens then. If 95% is here, that means on this half, what's half of 95%? 47 and a half?
Yes.
So if it's 47 and a half, this much is 34%, what's this? 13 and a half. And 13 and a half here. See what I'm doing here? I'm breaking it down into percentages because you'll start to see when you want to say, hey, within standard deviations, what's going to happen? You can do percentages because then that's your probability of things occurring. Within 3 standard deviations, you get 99.7%. So that's a lot more. So that means you have, what is that? Within 3 standard deviations, it's 2.35%. 2.35. And then your outliers, the last little tails. So if you've ever seen the t-shirt on a, I've seen this before. What was a bumper sticker or a t-shirt? I've seen this as a t-shirt or a bumper sticker or something along those lines where it says that I am here. That means I am at the top end of all data sets, which means I am the top 0.15% of people on a normal curve. So if you want to think of it in terms of scores and things like that, you're the top 1% of 1%.
So you're saying
Yes. It's a very smug way of saying I'm better than you.
that no one will
I'm
understand.
better, and you know.
Right, and I know that. Because why? I am here.
Been watching race.
I feel like
I know.
90% of people. Yeah, you're in running shoes.
I'm not in my running shirt.
It's okay.
You were
T-shirt
t-shirt
under.
Yeah.
He says funny stuff.
There's still another week.
Wait, so after 13.5, it's 2 point what?
235, and then out of the very end, it's 0.15.
Why is it 2.3? Oh, because it goes to 90.
It goes 90. This is 99.7. From here to here is 99.7. I'll draw this up a little bit cleaner. So you see percentages.
Oh, okay, I know, I see what it is.
They always take something.
So what happens here is that we're going to be able to take information like this. A survey shows that time spent in the supermarket is normally distributed with a mean of 45. If you have a mean of 45, that means it's the what? It's the average. So a survey shows that the average time spent in the grocery store is 45 minutes with a standard deviation of 12. So for every standard deviation of 12, I'm adding 12 minutes to 45. So if I'm looking at a curve, I can't even draw this. If I'm looking at a bell curve, my average goes in the middle, 45 minutes. When I'm adding standard deviation, every time I move over one standard deviation, it says my standard deviation is 12, means I'm adding 12 minutes. So here would be, well, what's 12 plus 45? What's 45 minus 12? That's plus or minus 1 standard deviation. 68, what that means is that 68% of people surveyed are in the store between 33 and 57 minutes. That's how that works. That's how the percentages work themselves out for probability. So if you randomly select one person out of the survey, the probability that they are in the store between 33 and 57 minutes is 68%. Because 68% of all data will occur within 1 standard deviation. Okay? If I add another 12 minutes, I'm at 69 minutes. If I subtract 12 minutes, I'm at 21 minutes. That means within 2 standard deviations, 95% of people surveyed are in the store between 21 and 69 minutes. Start thinking about that, kind of makes sense. Yes,
Is
sir?
it always going to be those same percentages?
Yes, those percentage, that's what's great about normal distribution, the percentages don't change. The data sets will, your mean and your standard deviation will change, but when you're within the realm of one standard deviation, plus or minus, it's always 68%. 2 is always 95. 3 is always 99.7. Always.
It's a 97.
Was it 97.5?
That was 99.
That was 97.
99.
I know the last.
We're gonna double check that because I bet you we can find it in a book. I just made that up. You don't know where to look, let's look in a book. Super readers, to the rescue. Or is it super wide? It's super, what do they call it? Super reader, super. Yeah. Yeah.
That was a pretty killer show.
You know what? If you guys want to make any money in life, you need to come up with a children's show that all you have to do is come up with about 6 minutes of new material, and then you can replay the opening credits, the middle credits, and the ending credits each and every single episode. Because if you look at most children's shows, that's how it works. Everything is the same to start, everything's the same to end. In the middle, there's always some sort of a song, or let's go do this, let's do that. That's the same each time. Only thing that's different is a little bit of dialogue, about 6 minutes worth of material. I'm telling you, there's a lot of money to be involved. I mean, think about it. The guy that came up with Dinosaur Train, seriously, gold mine. Kids love dinosaurs, kids love trains. Hey, let's merge the two.
Dinosaur.
I feel like you can do that with anything.
I'm telling you, you know,
What do kids like?
Toys.
Power Rangers.
Power Rangers. How many different Power Rangers?
Power Rangers, me, Teenage Mutant Ninja Turtles.
I'm telling you, Power Rangers, for some odd reason, and again, the start of Power Rangers shows, they're all kind of the same, and then they go to some warehouse in Southern California, have a fight, and then they go back to the same station. The sets don't change, you're still fighting the same box person with claws.
And then they have different Power Rangers.
No, one
Different
type.
types of
The other one that does the same, it's like the same thing over and over again was,
Little Einstein.
One.
no, my kids just started watching Mod Squad.
We're not that big.
It's the same thing over and over again. There's no variance, but the kids eat this stuff up. The people that are coming up with these ideas, I'm telling you, get an idea for a children's show. You're in childcare, you know what kids like.
I don't know. I don't know what kids like nowadays.
Legos,
I don't know.
Nerf guns. If you can make a Lego shooting Nerf gun. Anyway, back to normal distribution. What?
Lego shooting.
It happens third hour too. Same stuff. My mind goes crazy. I don't know what I'm talking about.
I never was good at Legos.
That would work too. Anyway, so we're almost done. We're almost done.
I want to come home.
Another standard deviation would be added another 12.
I was a Lincoln Logs kid.
Yeah.
That'd be what, 81? And then this side would be 9?
Yeah, I've heard of it.
Okay. And then you have your outlier stuff. So right here we have our average, our mean. A lot of times I'm going to show that with an X with a bar over it. Standard deviation, I believe this book does that.
What is that?
It's
It's like
it'll have it written as the mean plus that theta, mean plus 2 of that, so it's telling you you're going up and down
That's
standard
theta?
deviation. It's like, I think it's lowercase theta, I want to say.
Wait, there's a lowercase theta?
Oh yeah. Just like there's uppercase, lowercase, regular alphabet, there's uppercase, lowercase, Greek alphabet as well.
Why is it just an uppercase theta?
I don't know, I wasn't there when they made this stuff up, I'm not that old.
Well,
Gotcha.
I knew somebody was going to say something.
Oh, Mel's. Oh, Mel's. Good old Mel's.
I like the
That was good. All right, so go back to our percentages. We go back to our percentages and check this out again. Let me actually just bring in the percent piece so you can see it. So what they're doing here is they're telling you that certain percentages are going to occur within all of these. Now, what percentage of shoppers at the supermarket will be between 33 and 57 minutes? So percentage of people between plus or minus 1 standard deviation was how much? 68%. Because what we've done is we started with our average amount of time, brought it out of standard deviation, plus or minus 1 standard deviation, always equals 68% between the two. What is the probability that a randomly chosen person is between 45 and 69 minutes? Well, we have to go back again, saying that I know this was 34, and then this side was 13.5. So between 45 and 69 minutes, I have what probability of picking a person? 47.5% of people. That's what we're looking at. Yes, sir.
And you know, like I know, but why do you know it's 13.5 for the next?
It always is. It always is. Yeah, let me draw this out a little bit larger for your percentages. So here's our average. Within 1 standard deviation on both sides, 1 plus, 1 minus. This side is 34%, the other side is 34%. That's why we say within plus or minus 1 standard deviation is 60. I'm Danger Will Robinson. Is 68%. If I go up 2 standard deviations, or I go down 2 standard deviations, I know that the overall between the two was 95. So we cut it in half to get this side, subtracted 34, and we got 13.5, which is mirrored on the other side as well. Then if I go plus 3 and minus 3, we were 99.7, I think. Yes, ma'am.
Would you ever end up with a negative number?
What do you mean?
The second side of, oh, never mind.
Like, see,
So what did we wind up there? That was within, after 2 was what? 2.35? And 2.35. And then, yeah, 2.35. And then after anything greater than 3%, just going the other way out, I mean, to our, what we call an outlier, this last spot was 0.15%. Well, that's just the decimal value. I'm making it, I just put in the percentages. That's just decimal, I'm just putting this in percents. And the other side here also would be 0.15% left over as well. So anything above 3 standard deviations, that just means that in this data set, 0.15% of the time of people surveyed spend more than 81 minutes in a grocery store.
Who spends that much time in the
My mom.
depends on how much you know.
To be honest with you, if you start thinking about it, if you're just gonna go grocery shopping, I mean, this seems like a weird data set, but nowadays, if your folks are anything like me, I'm sorry, but if they go grocery shopping like most families do nowadays, you go to multiple stores, right?
Why do you want to trip?
Yeah, you stop at a couple different places. You know, some place has one thing on sale, some place has something else on sale, and you go to some other store for something else because the selection is better. So you go through a couple of different stores. So it's tough to say that you have 45 minutes at just one place nowadays because we have such a greater variety. So this is an old textbook, but you get the idea. Okay. Do we know?
Sure. The kids are getting a new textbook though.
Yeah.
Is it like updated like 2016?
What's that?
Is it like updated in 2016?
I think it's a, I forgot the year, it might be a 14 text, but I'm not sure, 14 or 15. So according to the survey of National Center for Health Statistics, the height of adult men in the United States is normally distributed with a mean of 69 inches and a standard deviation of 2.75 inches. If you randomly choose 3 adult men, what is the probability that all 3 are 71.75 inches tall? See you, Shorty. It's a joke. This is getting tall.
I'm still below average.
You too, buddy. Take it easy. All right. Nowadays, somebody Google this for me. I bet you this has changed. Find out what the average height of a male is now. Well, yeah, because 60 would be 5 inches, 5 foot, 9 is 5'9". I think it might be higher. But anyway, so if it says that our distribution is normal,
It is 69.7 inches.
so it's gone up a little bit. And that's normal. You start to see that a little bit over time. So if we started again,
Basically 5'10",
you start at the average height is 5'9", and it gives you a standard deviation of 275. What's 275 more than 69? 71 and so 71.75. And then if I subtract it, I'm back to would be 66 and a quarter. Yes, sir.
The standard deviation, that's how much you either go up or subtract from your.
Yes, sir.
So these are gonna look the same every time.
Yep. Only thing that changes is your numbers, and that's what's great about normal distribution because it's normal.
Cool. All right.
Cool.
So what? 66 and a quarter.
Yeah.
Add another 275, you get what? 7450?
Yeah. 70.
Is that right?
Sounds basic.
Sounds good now.
Yes.
So no, 7350. No, 7350.
And then you get one more. It's basically the same.
The survey is 7350.
I know you.
No? Carry the one. Add another one, we're at 7725.
Yeah.
Sure.
Going back the other way, subtract it out. 6350.
So,
Yes.
this is where a calculator comes in.
Calculator is schmelculator. And then 61 and a quarter.
Yep.
60 and a quarter. 67, all right. Okay. So basically, that gives us our stuff. So now, think about what that is in terms of height. 71 inches is what? 5'11 and 3/4? 5'11 and 3/4. 74 inches, 74 and a half inches is 6'1.5".
Yeah.
Okay.
That was
77 inches is now, so this is 6'1.5". Add 2.5 inches, that's now you're at 6'3" or 6'4", no, 6'3 and 3/4.
Not 62.
Yeah, isn't it 62 and a half?
So then we're at 275, so it'd be 6'5".
So we just said Jen.
Only 74 inches.
So you start thinking about it. You're 6'3", right?
6'2".
No, you're 6'3", I'm 6'3".
And I'm 6'2".
So you start thinking about being 6'3",
Wish I was.
you know, just start hanging from the rafters
Okay.
by your feet.
The last time I did that, I dropped a heavy from the bench.
Just stretch.
So here's 34, 13.5, and then 2.5. 2.5, right? 2.35, 2.5. As you start thinking about it, if you back the rest of this up, how much is on this side total? 50, right? According to just this data set, if you start to think about this, myself, Cole, Edgar, you're about the same height too. You're about 6'3", right?
Like 62.
Okay, so the three of us, just looking at that being, if 6'3" is 75 inches, right?
Yeah.
We're in this range here. according to this data, just the three of us alone are taller than, well, what's 100 minus 2.55?
97.
27.4.
We're taller than 97% of all males.
Ooh, sweet.
That makes me feel a lot better about myself.
When you start thinking about the data sets that are out there, if we're within these, if these standard deviations are still holding true, I don't know if they are or not, that means I'm taller than 97% of all people. But that's what this stuff means. That's what normal distribution looks itself at. That's what's so cool about normal stuff, is that you can start playing around with stuff like this. You can look at real life statistics and see, where do you fall within the set of averages, the law of averages? Where are you falling in this play? That's why they norm test data. That's why you can see where are you according to other sets of data. How far are you from the mean? Where are you in relationship to other people that have taken tests? That kind of stuff. That's what's so cool about norm stuff. So now the question is, according to this data set, what is if you randomly choose 3 adult men, what is the probability that all 3 of them will be 71.75 inches or taller? So the probability that one person is going to be 71, 75 or taller, isn't that everything to the right of this? Well, going this way is how much percent? 84. So the right of it would be how much? 16. So I'm looking at 3 people in a row at 16%. So wouldn't that just be 1/6 cubed? The probability you choose 3 people that'll be taller than that, you have 16% of possibility of picking that person. Well, if we're picking it 3 times, 0.16 times 0.16 times 0.16. That's how that works.
0.004.
Not a good chance, is it? Yeah, we did it this class. Well, we actually had more, really.
So
You start looking at,
Like 5.
you look at Sauter. Sauter's what? He's 6'5"?
Why do you say you're 6'4"?
6'4", 6'5".
Okay.
It doesn't matter.
You start getting over to here, you start talking about taller than 1% of population. It's crazy when you start looking at this norm data stuff. I just think this stuff's kind of cool.
That's because you're part of the taller 97.
Well, then short people, if you're a 5-foot male, if you're a 5-foot male,
You are really, really short.
well, it's not that you're short, but well, yeah, you're
No,
short.
you're short.
No, you're
You're
short.
short. 5'10".
If you're shorter than 5 foot, hey, you're like in the 1% club.
Yeah. May not be the top 1%, but you're in the 1%.
You're definitely not the top of 1%.
I know.
Short.
Way over.
Joe, short.
Bottom.
So, like 5'8", I'm almost average.
Okay, no, you're not. Raise my hand.
Just below.
What's like the legal height to be a midget?
I think it's under 5.
I think you're right, because you can, if you are a certain height, you could get special privileges for parking and stuff like that. Because yeah.
What about if you were 1 foot, you get a privilege for that?
Technically, when you're a midget,
Could you get a privilege? I think there's something that if you get like a parking pass, because I have one.
Does it affect your driving?
It's so stupid. Just, I wouldn't do that.
The possibilities are better.
It's 4'10".
Is it 4'10"?
And the average height for a male in the world is 6'1.1". The 5'9" is white males in America. So you guys aren't that special.
We're pretty special.
Talk about crushing my hopes and
I just look
everything. You're just not that special.
I just drop it down.
We're still above average.
I'm still below average.
There is one thing they talk about the bino. You can do bino. Let's do these.
No. You said you didn't want to learn. Can we only do like 4?
Is this on I got
I'll do this one.
Oh my goodness.
All are even.
There's 4 scenarios. There's 4 scenarios and there's one binomial distribution problem that's thrown in there for good fun. Yes? What I'm going to do with review stuff is that I have a couple of different paper versions of things that I've done over the past few years. I kind of knew where I was winding up with these things, and I've had a runoff for a long time. And I just knew that I didn't want to, I hate to give you guys stuff too soon.
We hate getting stuff too soon.
So, and some of the stuff that we've talked about and done, we haven't, it's just so hard to find extra review problems of, because we've kind of done everything that I could find. You're sassy today. So what I would suggest is that I have the problems. I'm going to post, I think I will post all the answers on the website so you can have all the answers and double check them through. I have 3 different sets of problems that we're going to look at. I'll give you guys the first grouping today. I'll give you the next grouping middle of next week, and I'll give you the final grouping for the final weekend leading up. I still want to test chapter 12 Tuesday. So we'll come through this stuff. We'll talk about it, tie everything back together. We'll go through. We'll review cards, rolling dice, and all that kind of stuff on Monday, and then we'll take our test. I got a 10-question test on this stuff for Tuesday, and then come then Wednesday, Thursday, Friday, Tuesday, we got 4 days of review, which is more than I anticipated, but it's fine.
So the top.
Okay.
Could be even.
Does that sound good?
Yeah.
Well, I hope so, because that's what we're doing. Yes, sir.
So